Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera again. Okay, so this session is to address some queries by some of you regarding the previous task that I want you to do, which is to fill in the blank in the table of handout number 2 as shown to you here. So we have done in a systematic way the information regarding Cartesian coordinate as well as cylindrical coordinate, and I did purposely ask you all to fill in the information in this particular column regarding spherical coordinate. And it seems to me some of you found a bit difficult to do it, maybe still not confident, or maybe some other reason. So let me show you how it can be done using the same approach that we have seen in our previous coordinate system. Okay, so let's do it together systematically. Hopefully you can see how easy it will be. So now we're going to talk about the third coordinate system, which is spherical coordinate system. Okay, so that should be our interest here. Okay, so the point P, I'm going to indicate the point in space in this coordinate system. So why I'm using the symbol P? Just to remind me, this is the same position as what we have defined in the Cartesian as well in the cylindrical. But since we are using spherical, the variable that we're going to use to represent the position now will going to consist of different variables, which are the first one should be R, the second variable going to be theta, and the third variable going to be phi. So that should be the typical variable that we use to represent a point in space based on spherical coordinate system. So let's draw the position now, okay, using our new coordinate system. So I'm going to draw the typical axis that we use in Cartesian. But now, since we are dealing with spherical, we're going to draw a sphere now. So that should be our spherical structure. Okay, so this is going to be our x-axis, y, and z. I'm going to draw a longitudinal line this part on the surface of our sphere here. So the point P is going to be located at this position. So I can see is exactly the same as what we have shown in the Cartesian as well as in the cylindrical. So let's define the R with regards to the diagram here. Okay. So the R, as you can see, indicate the radius of the point P from the origin of the sphere or the center of the sphere. So that should be our R variable. And you can see the R can change according to the position P. If the P shift moves somewhere else, so the whole surface of the sphere going to be shifted as well. Therefore, as you can see from this particular diagram, the R range must be from 0 up to infinity. Okay, R cannot have negative value. If R equal to 0, meaning that the point P is located where? Yes, at the origin. Now, the second variable here is theta. Theta is defined as the angle that we must refer to according to this longitudinal line. So what's our theta meant here? Theta is the angle starting from the z-axis. You move it until it's arrived at the radius of the sphere. So this should be our theta. Okay, so the reference should be the positive z-axis, and you move along the longitudinal line until you arrive at the radius of our P. And there, the theta should be defined as from 0 and only up to pi. So it cannot be 2 pi, it's only up to pi. So that's by definitions. And finally, the phi. Remember, when we define the phi in cylindrical coordinate, the phi must be measured where? Yes, on the xy plane. Okay, so therefore, the way we define the phi, we must project the radius now, so that the radius are going to produce an image located on the xy plane. So that should be angle 90 degrees. So that should be the new image of our radius on the xy plane. And the phi, as what we have done in cylindrical, we're going to start from the x-axis, move towards the image now. So that should be our phi. So it's exactly the same as what we have done when we define the phi in the cylindrical coordinate. And therefore, the phi should have the same definition in the cylindrical from 0 up to 2 pi. Okay, so that's how you define our phi, r, theta, and phi. So next, we want to determine what should be the unit vector, because now you want to express the position in terms of vector. So the vector now must consist of the direction r, theta, and phi. So r, as what we have seen before, should be extended along the radius of our point P. So that should be positive r. So positive r means that the direction is moving away from the origin, whereby negative r meant that the direction towards the origin. Okay, the theta now must follow the pattern of angle theta. The angle theta move in this direction. So it's a circle now. So the direction of theta must be tangential direction. What it meant by that should be this direction theta. So this should be positive theta. So it's making angle what to the r? 90 degrees. That's what we mean by tangential direction. And for the phi is actually the movement down here on the xy plane, which is in this tangential direction. So we can move it up here to be parallel now. So that should be our phi directions. Okay, all these three unit vector making angle 90 degrees to each other. So then what we did, we going to draw a box. The box going to represent a small variation of structure, and from there we're going to extract the information so that we can fill in the blank space here. So that's going to be the next step. So whenever you're going to fill in this space, must based on the box. The box going to be drawn based on this unit vector. So let's do it together now. Okay, so I have to draw it slowly so that you can see it's overcrowded already. Sorry about that. So I'm going to use this unit vector as my foundation of my box. Okay, so let's draw it. So this should be the first one I can see. Then I'm going to follow the next one. Okay. And I'm going to draw the dotted line here. So that's going to represent our box. Okay. Hopefully clear to you. Sorry about the mess. I'm sure if you look at it carefully and slowly, you can see. Maybe your drawing is much better than mine. Eh? Okay, I'm going to give the dimension to the box now. The simplest side first, this side. What should be the length of this side of the box? So the answer is very simple, because this side depends on the r. Therefore, the length should be dr. Agreed? Okay. Whereby this side now, as we can see, is depending on the theta. And we can see the radius here is r, therefore the length should be r d theta. And the last side should be this side now. So remember, this side actually based on information actually located where? Located on the xy plane. Okay, so this side and this side should have the same length now. So whatever information you want to determine here must be based on the information gathered on the xy plane. Okay, so now what we can see now, the radius here is no more r, is smaller than the r. Okay, and the radius actually is equal to r sine theta. Do we agree on that? So the length on the xy plane of the r now going to be the projection length, and we're going to define that to be r sine theta. And the change of angle here is d phi, therefore the actual length here, the radius multiply with the change of angle, so it should be r sine theta d phi. Okay, that's done. See how simple it is? Still based on the same principle that we've seen when we derive for the information in Cartesian and cylindrical, but we must be aware of what the definition all about. For example, as I mentioned before, when we define the phi, the information must be located where? On the xy plane. So therefore, you must try to find the information at the proper location. Okay, now let's go to the first definition that we're going to define here, which is differential line length, which is this term here. That's what we're going to do together. Okay, so now we're going to take the most critical cases where it's going to be from this location, move to this location. We call it P to P prime. Okay, so I'm going to move from P to P prime vector. So therefore I'm going to draw the vector now. So from here, I'm going to move to this direction. So that should be the vector we are going to define now, P to P prime. So I'm going to follow logically three different paths. The first path I'm going to follow going to be based on the r component. Then I'm going to use the theta component. I'm going to end with the phi component. And you can translate that into equations such as, for the r component should be magnitude dr along the r directions. Okay, from here to here, magnitude dr, r direction. Then I'm going to follow this path now, magnitude r d phi. Since moving downward, you can see it's positive theta. So plus d theta in theta direction. I'm always confusing between theta and phi symbol. Sorry about that. And finally, I'm going to follow this phi component. Okay, so magnitude r sine theta d phi, since this direction is obeying this positive sense of phi. So plus r sine theta d phi directions. See, inshallah, it's very simple if you understand the steps. So therefore, please fill in the space here, drr plus r d theta, theta plus r sine theta d phi. Okay, so that's what we should do. I believe most of you able to do it, inshallah. Yeah, so then we're going to go to the next task now, to define the surface vector. So what's important here, the way we numbering the surface. When you number the surface differently, you're going to have different solution. Therefore, I'll try to make it consistent such that it's always obey the sequence r, theta, and phi. What I mean by that, I'm saying to myself, this particular surface that we can see, I'm going to label as surface number 1. Okay, so this particular side of the surface of the box here, I'm going to label surface number 2. And finally, the area that I can't see on the far end of the box, which is the other side here, okay, I'm going to label as surface number 3. So I'm going to put angle arrow there rather than dot to indicate to me I can't see it. It's the other side of the structure. Okay, again, surface number 1 on the top here, surface number 2, this particular location, surface number 3 on the side that I can't see. The reason I do this just to obey the sequence of r, theta, and phi. Therefore, what should be surface number 4? Opposite to surface number 1. Surface number 5 opposite to surface number 2, and surface number 6 going to be here, which is opposite to surface number 3. Okay, let's define the surface vector now. Okay, so ds1 now. So, therefore, what I'm trying to say now, if you choose numbering slightly different, meaning that instead of you number 1 at this particular surface, you choose number 1 to be somewhere else, therefore your solution should be different than mine. Okay, so the numbering, the answer that we going to get based on the numbering that we place on our structure. So based on this particular example, since I number 1 to be here, therefore my solution will be based on this particular diagram. Yeah? So what it should be here, the magnitude now should be this length, r sine theta d phi. I'm going to multiply with this length, which is r d theta. So therefore, it's going to be r square sine theta d theta d phi. Agreed? That should be the magnitude. And since the unit vector here, which normal to the surface here is r, so it should have directions r. Okay? So let's repeat with the surface number 2, ds number 2. So what we can see here, the area here should be r, okay, sine theta. I'm going to multiply with the length here, dr, therefore I'm going to put here dr d theta, okay, sorry, d phi, therefore I should be careful now, in the theta directions. Okay, r sine theta d phi, multiplying with dr, I'm going to get r sine theta dr d phi, theta direction, because normal coming out from this particular surface number 2, obeying this direction, positive theta. And ds number 3 should be equal to this length, multiplied with this length. Therefore, should be r dr d theta in phi directions. Is it correct? R d theta multiplied with dr should be r dr d theta. And for ds number 4, going to be opposite to ds number 1. I'm going to write it to be ds number 4, sorry. Going to be negative of ds number 1. Similarly, ds number 5, going to be negative of ds number 2. And lastly, ds number 6 should be negative to ds number 3. Since we have only 6 surfaces, therefore, logically, they're only going to be 6 different surfaces that we can define now. Okay, the last variation or information that can be extracted from the movement of P to P prime, according to the spherical coordinate, is the volume. And we can state clearly now the volume here, dV, is going to be all these three sides multiply together, and we're going to have here should be r square sine theta dr d theta and d phi. So with that, we can we can fill in the blank completely now. So what you're going to have now, a complete table that we're going to use as a reference later on throughout the course. Because you can see later on most of the structure that we're going to solve problem, the information can be extracted from this table. So please remember, this table is important because we're going to use it throughout the course. Therefore, with that, I would like to thank you for those who asked me about this. So what I'd like you to do next, whenever you ask me question in future, please write in detail what actually you don't understand, so that it's easy for me to tackle the issue, rather than just give blank statement that you don't understand. So please help me to help you by detailing what actually your concern. So therefore, I can address that concern specifically, because I don't want it to repeat some tedious thing that you already know. Okay, so with that, thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.